Okay, all right. Part 4 is probably the most important here. We're going to understand the conservation of energy. So we're going to have a column for gravitational potential energy, elastic potential energy, and kinetic energy. And if you add all three of those up, you should get total energy, and that total energy never changes as it's oscillating back and forth. We're going to use a 250 gram mass. We're going to put friction on none so that it's not losing any energy, so it'll completely oscillate back and forth, forever in our applet. We're going to measure these three types of energy every 5 centimeters that it drops. So if we come down here to part 4, we're going to do a height that we're going to drop from. We're going to get a displacement that we're pulling the spring. We're going to get gravitational potential energy. We're going to calculate elastic potential energy. And then whatever is left will be our kinetic energy. And then we also want to figure out what's the velocity at various points during the fall. So all we really need to do here is we're going to take this off here. We're going to turn friction to none. And I'm going to take a 250 and I'm going to put it on here. Hook it on and make sure that you're lined up there straight. And I'm just going to drop this. Okay, I'm going to drop it. And there it goes. Whoops, I'm still on planet X. I need to be on Earth. Let's try that again. Go back onto X. Take it on there. Drop it. Okay, and I'm going to kind of close this like 1/4 time. And when it gets all the way to the bottom, I'm going to try to pause it and see how far it falls. That wasn't very good. Let's do 1/16 time. Okay, almost got to 50. We'll go ahead and call it 50. We'll say that it dropped 50 centimeters. Okay. So the height that we're dropping it from, what we're going to say is 50 centimeters, or actually half a meter, 0.5 meters. And then we're going to drop it 5 centimeters each time. So this next one here then would be equals this minus 0.05. And I could take that and I could drop that all the way down till it gets to be 0. I went way too, oh my. I gotta undo some stuff here. Okay, take this. Gotta go a little farther. Totally messed it up. Undo again. Okay, and this last one should be 0. It's basically 0. I'll put in a 0 instead for it. Okay, so this is how it's going to fall 5 centimeters each time. So after it's fallen 5 centimeters, this is how much height it still has. And here is the displacement that we're actually pulling the spring. So at the beginning, we haven't pulled it at all. And then here, we will do this, this cell plus 0.05. We're going to add 5 centimeters on each time. I could grab both of those and pull that down, and that takes me up to 2, 3, 4. No, that's not good. Don't know why I did that. 0, okay, equals this plus 0.05. Guess all I need to do is drag that one down. There we go. So it's going to eventually pull the spring half a meter. Here it's falling from half a meter down to 0. So we want to figure out our gravitational potential energy at the top. So at the top, before we dropped it, all the energy is gravitational potential. It is not stretched to spring at all, so there's no elastic, and it's not moving, so there's no kinetic. So just to make sure we remember the formula, is gravitational potential is mgh. And elastic potential is 1/2 kd squared. And kinetic is 1/2 mv squared. Okay, so what's the gravitational potential energy at the top? Well, it'd be equals the mass, and what are we putting on here? We're putting on a 250, so 0.25 times gravity, which is 9.81, times the height, which was right here. Hit return, and that is the total gravitational potential energy. Okay, what's elastic potential energy? Okay, well that is equal to 0.5 times the K constant, which is here, and we want that every single time, so we need to, I don't know what I just did there, 0.5 times, I need to do $sign K times D, which is this, squared, 1/2 kd squared. And you'll see at the beginning there's no elastic potential energy because I haven't pulled the spring down at all yet. Kinetic energy then is going to equal your total energy that you always have, subtract out all three of these. Well, the total energy we're going to have at the beginning is 0.122625. So equals 1.22625. And I'm going to subtract gravitational potential. I'm going to subtract elastic potential. And whatever's left then should give me my kinetic. And of course that's going to be 0 at the beginning also. Okay, so what I can do is I can grab those and I can pull that all the way down. Okay, so you'll see I have gravitational potential energy here. At the bottom I have almost that amount of elastic potential energy. Technically I should have that amount, and that's because my K value is off just a little bit. My kinetic energy is 0 at the top. It starts to speed up. It gets up pretty high up here in the middle, and then it starts to go down again and gets back down to 0 again. We could figure this out and make this perfect if we figure out what our K value really is, and that would be mgh. So so at the beginning we had 1.22625, and if we equal that to 1/2 kd squared, use that formula there, we could solve for what the K technically should be. So what is that going to be? That's going to be K would equal okay, I messed this up, equals 1.22625 times 2 to get rid of the 1/2, and then divide by D, and the D we dropped is 0.5, so 0.5 squared equals. So the K value is actually 9.81 for this, to make this work out perfectly. So if I come up here and I change that to 9.81, okay, that'll actually change my masses, 306, 160, 70, and it'll make this work out. So I have total gravitational potential energy up here. That's how much elastic potential energy I have at the bottom. So it swings between this, and the kinetic energy goes up and then back down to 0. So what I want to figure out is the velocity. How do I figure out the velocity? Well, Ke equals 0.5 mv squared. So how do I solve for the velocity? Well, it would be equals 2 times the kinetic energy, which is this, 2 times kinetic energy, and I'm going to divide by the mass, which was 0.250, and then I need to take the square root of that whole thing. So the way I'll do that is SQRT and have that whole thing in parentheses, and there's the velocity. And I can take that and drag that down, and you'll see this velocity at the beginning is 0, and it starts speeding up, and then it gets to a maximum right here, and then it goes all the way back down to 0 again. At the bottom, it would be 0 again. So right there, I can kind of highlight that. Okay, right there is max V, and that's important because it's halfway down. Halfway down is where you're going to get a maximum velocity of the weight. It's going to speed up, and then it's going to start slowing down again because of this conservation of energy the whole time. Okay, so where number 5 is where is the kinetic energy at a maximum and what is the velocity at this point. We just did that. 6 is we're going to look at this graph and we're going to look at some energy. So I'm going to unpause it. We'll go back to real time. I can show energy of number 1 right here, and this is kind of interesting. You'll see. Well, let's do it in a quarter time. So from here all the way up, we have a big column here, but even though there's some different colors in this column, total energy all the way up to there. So at any given time, parts of this total energy are different. So if you look at this one, when it's all the way at the top, once it gets to the top, it'll have 0 kinetic energy. As it goes down, its kinetic energy increases, and then it gets all the way to the bottom, and the kinetic energy goes back to 0 again. Kind of watch that for a little while. Watch this thing and see how much kinetic energy it has at any given moment. Let's skip this one for a second. Elastic potential energy, you'll notice that at the top, right there, has none, and as it goes down, it creates a lot of elastic potential energy because it stretches out the spring. The last one is gravitational potential energy here in the middle. You'll notice it never gets all the way down to 0. And that's because where the frame of reference is that you're measuring. We measured from how far down this got. That was our 0 line. They're technically measuring from like down here below on the floor. So no matter what, even if it gets all the way down the very bottom that it oscillates down to, there's still some gravitational potential energy here. Okay, so as it goes all the way up, it gains a lot of gravitational potential energy. And if anywhere down here in the middle, I pause this, I could take this graph, this bar, and this bar, add them all together, and I would get this bar here, total energy. So total energy remains the same all the time, but the different parts of it change. I can unpause and then pause it again and see now you have a little bit of elastic potential because it hasn't pulled it very far. It has quite a bit of kinetic because it's actually starting to move pretty fast, and it has a lot of gravitational potential energy because it's still way up here in the air. Let it go a little farther, come back down. Kinetic energy is even bigger because it's still going down. Gravitational potential energy less. Okay, go a little farther. There we go. Okay, and all 3 of these things always add up to the total. Now I can go back to quarter time and I can start maybe adding some friction in. And what you'll notice is that now there's another energy, thermal energy, and it just is going to continue to start to increase and take more out of this total energy. So some of these other ones will start decreasing over time. I can add a little bit more friction in, so it'll grow a little faster, and you'll notice that velocity is going to start slowing down, kinetic energy gets less and less, and so the friction, the thermal energy, is taking more and more out of our overall equation. So the conservation energy, technically only works when you have no friction within the system. Within the system, you'd be losing some energy if you have some friction. But overall, all the energy is all still there. Eventually, see, we get here, we put lots of friction on there, and this thing is going to come to a complete stop. There's no more kinetic energy. There's still a lot of gravitational potential energy because it still could fall. And there's a little bit of elastic potential energy because it's stretched the spring out, this far. So that energy is all still there, but there's a lot of heat that has been created in the air molecules and within the spring itself. So that energy is really not accounted for anymore. That's all kind of out in the surroundings. So in your last section, this number 6, that would be a good thing for you to explain these charts and stuff right here for your QED statement at the beginning. So what you'll want to do is you'll want to print out this whole Excel sheet and cut it out nice and neat, hopefully smaller than your actual page, and paste it into your inquiry book for your lab. Hope that makes sense.